Let's move on to the next presentation, which title is From TC10 to System Wake-up Safety System Solutions. Steffen Lorenz from NXP, please.
Yeah, thank you for the introduction. I'm Steffen Lorenz, System Architect at NXP. And yeah, so TC10 is probably known to a lot of you. And so for those who do not yet know, you will know after the speech. It is about sleep and wake up. And so there are a lot of needs to put things to sleep, especially if they are not needed. It doesn't make sense to consume power. And but there's also a system point, a safety point of this. So if you switch off things, then you cannot rely on them because they are not on. And so this is what I will talk about. I will start with the introduction and the motivation. So why are we doing this? And then we'll go into both the sleep and wake-up concepts, so briefly look into what is TC10 about, and also the functional safety for Ethernet specifically. And then coming to some system aspects to see, okay, especially in a zonal architecture, what does it mean, and close then with a summary and a conclusion. Yeah, you already saw this kind of drawings quite some time today, and you probably will see it over the day and the next day again and again. So what we see is that in the industry, it goes from a domain-based architecture into something which is zonalized. It happens in different steps, but yeah, we see it happens, and with this there are new challenges coming up. So if you look to the wake up specifically, then in a domain-based architecture, you have the function itself in the domain, and if you need to wake up something, it's mainly in the domain. So you handle everything in the domain. And only if there is something which is needed to be transferred to another domain, then you have the gateway in between. Now if you go to the zonalized architecture, and you see this in this picture, the colors which were domain-based before, they are spread all over the network. And this means if you want to realize a certain function, you will need to have services of your zonal gateway, or maybe also of your central brain. So it is all spread over the complete network, and with this you need to handle the wake up and also probably functional safety in a different way. So if we now look closer into those zonal gateways, let's talk about what is the function of such an aggregator. So it is aggregating the data, and it has a gateway function. So it brings data from one technology, so CAN, for example, into others. And with this, it also has some different technologies. So it has Ethernet, could also have multi-drop Ethernet, like 10BASE-T1S, CAN, and much more. We will later also look a bit to this. On the other side, it connects to a high-speed backbone typically, and if you want to send data to another part of the car, this backbone is needed. And all those connections, they belong to different functions. There's much more that it does, but it also consumes power. And this consuming power side, of course, is the disadvantage, and especially if you don't need something, you should switch it off. But as I said in the beginning, if you switch it off, you also need to consider this in your safety concept, that those parts can be off. So if you now look into the part switching off certain things, there is a standard defined which is often called TC10 sleep and wake up. And why is it called TC10? This comes from the Technical Committee 10 of the Open Alliance. So this technical committee is or was specifying the standard, and it is currently specified for 100 base T1 and for 1000 base T1. It is also going to be defined for higher speeds, and also for 10 base T1S there is work going on. In this case it is a TC14 because this one is defining the complete standard. The 10 base T1S is fully on physical layer defined, on phi level defined, and if the link should go to sleep, this of course involves the network management, so there must be a trigger to go to sleep from the application side. But the handshake to really align on going to sleep, this happens on the phi level. And this is really per link. So in a network you can have a partial networking because you can just put off links which are not needed. Then of course you also need to wake up, and for this there is also a fast wake up implemented which goes via the phis. So it is not needed to wake up the switches, but you just forward this by the phis. I will show it a bit more detailed on the next slide. So this allows for fast wake up. And it also allows to wake up over an active link. So you might have, like here in the middle, a link which is still active, but if you send a wake up from one part of the network, you also need to make sure that you reach, for example, this connection on this side. And so this allows for active but also passive networks to send the wake up. So if we look now more in the application, you see that it is phi-centric. So the wake up itself, it goes directly from phi to phi and is sent out there. You can have a switch which is allowing for more configuration of this, so that you can define from which way it should go to which other side. In principle, you use it to switch off ports or links which are not used, to prevent that they consume power. And this can happen individually, but if all ports are switched off, you would then also, or could then also switch off the switch because it is not needed anymore. The MCU, in principle, is independent from this, but by using the voltage regulator or the wake-up forwarding, you can also handle the sleep and wake-up of the MCU, being controlled by a local wake-up, but also by a remote wake-up. And of course, the complete ECU might be in sleep, and then you use the remote wake-up to wake it up again. So this on sleep and wake-up, and then coming to the functional safety part. So the functional safety is defined by ISO 26262, or it's not defining the functional safety, but the way how to reach functional safe devices. And it is a way to prevent unreasonable risk due to hazards caused by malfunctioning behavior of EE systems. This is how the ISO 26262 itself claims what they do. The idea of this is to look into the failures that can happen and see, okay, what would happen if a failure on car level happens? How often are you in a situation that this can harm? And would you have a chance to control it? You will see on the next slide that's all on the top system level, so typically on car level. But what is defined is, depending on the inputs, you get a so-called ASIL, so the automotive safety integrity level. And this gives you a a target point to see, okay, for this function, what is the risk that I can accept for this application? And let's see how this works. So for the function you're discussing, you take those 3 input values, and then there's a so-called HARA, the Hazard Analysis and Risk Assessment. I will not go deeper into this, but the important thing is that there are safety goals coming out at the end, and next to the safety goal there's also an associated ASIL. As I said on the slide before, this is performed on item level, and the item is typically the car or at least a major car function. So now how does it link to Ethernet? In principle, what is done then on the development, that this top level requirement is spread up down further to the actual technical implementation. And with this, you also inherit the ASIL and the safety requirements. And depending on which part in the car you're looking at, you assign them to different parts. And typically on Ethernet, you have those 4 safety requirements. So you must prevent unintended frame data insertion. You must prevent frame corruption, undetected frame loss, and unintended frame delay, repetition, or sequencing. So you should not get the same data several times without detecting this. Some of those parts are done in the application level, but especially looking to the zone, you see that there's a lot that can be done in the switches to support the system, making it safe, but also then making it high available. And we clustered this into 3 main directions that we handle this. So the first one is to prevent the failure. So if a failure is not happening, then yeah, it can also not cause any issues. And for this, we see on one end to have a high reliability of the product, to make sure that the failure rate is low. I will show a bit more on this on the next slide. Freedom from interference. So if you look into a switch, it needs to make sure that if there is a failure somewhere, you are not distributing this into the remaining network. And this brings me to predict the failure or detect it. So there are diagnostic features needed to make sure that you know about the data and that you can detect if something goes wrong. Otherwise, you do not have a chance to react on this. And this brings me to the last point. This is reacting on the failure. So you need to make sure that you can quickly react on the failures, so to make sure that within the fault detection time, you know where the failure is and you have the chance to react. And some of the failures can even be corrected. Before I go in more details on this, I want to mention that this is mostly talking about features of the product. But if you look to the functional safety standard, the safety definition or the design for functional safety goes far beyond the features itself, but it's also the way how it is implemented in the development process and how the organization is trained, for example. So let's quickly look into some possibilities on how to do this. So preventing failure, this is on one end the production quality. I show here one example from CAN. So there you see that if you take the norm, which is typically used to calculate the failure, then you get a certain failure rate. So 42 fit in this time. Fit means failure in time. When you look into what you can reach by qualification process, you see that the actual failure rate is, the qualification failure rate based on data you have from the qualification is already much lower than what you take for calculating the risk. But if you then look into the real failure rates which you see in the products, you see that with the right measures, you can really bring this down to a very low failure rate. And so this is one thing to make sure in the manufacturing already by the right processes, by the right techniques to find potentially failing products before and do not ship them, but scrap them. So this is one way. There are policing methods to make sure that you are not forwarding failures, and of course the configuration monitoring. So the things that the switch are doing is defined, but you need to make sure that your configuration stays as it is supposed to be. For the prediction of the failure, so you might have a built-in self-test to already find failures during startup, some monitoring, and you can or should have latent fault tests which allow you to detect that certain mechanisms you have in your products, if they are not working, so that you know if your safety features will really kick in if they are needed. And then finally, reaction on failures. Those are things like memory correction, so ECC, but you can also make it on network level, so that if you use CB for a certain redundancy, if then you detect that you cannot handle it, then you should enter a safe state to make sure that you are not sending corrupted data, for example. So this all, if you want to implement this, is of course also needs some involvement of processing of microcontroller, of software. And so let's see how this works in the system. And to discuss this, I have a very simple zonal controller with things which are typically in. So you typically have a couple of interfaces, so it could be Ethernet, there also CAN typically connected, LIN, maybe some GPIO ports. And they are connected either to the switch side or directly to the microcontroller, which is then doing the translation. Then there's typically a PMIC device or SBC, so some power device which is providing the power, but it's typically also used to supervise the ECU, so the MCU with the watchdog and also the switch. And the just discussed safety requirements, they are typically there on the communication, so you can have requirements for the switch side, but of course also the microcontroller has safety requirements. So now at the beginning I said we might switch off certain parts if they are not needed. So let's assume we have an application where you just need the communication. So this could be a charging case, for example. But it could also be if certain ADAS functions are switched off, when you say, okay, I do not need my data aggregation, I do not need the processing in the zone, but I just need to forward data which are collected zonally, and I need to send this to another zone or to the central compute. In this case, you see, the microcontroller is off, and maybe also the connection which is next to it. But the communication side is on, and you still need to have the functional safety requirements fulfilled. And this means that all your functional safety requirements must be implemented in the switch. You have part of the PMIC probably active because you need to have power supply. You might use some of the PMIC functions. But also on the PMIC side, you can switch off the part which is not needed, which is relevant to the MCU. So So this is one side, and this is probably the most relevant side because there are several applications where you might have this. In principle, it also works the other way around, so that you switch off the switch side, the communication side, but you just keep the MCU active, so that you maybe just capture data, or you're just looking for data which is coming in on CAN traffic, and then based on the requirement or the actual situation, then you wake up the communication when it is needed. I think there's not a specific use case to this, so you might have some local processing needed, but in principle it would work the same way as just having communication active. What you need to consider is that in order to, or if you go to sleep, you need to be wakeable again. So you might have different wake-up sources which come in and which needs to be considered, and depending on the way the wake-up comes in, then it is decided on what is needed. So do you only need the switch side, the communication part, or do you need the microcontroller awake as well? And how this can look like, I show on this slide, which is the last one. So in principle, just as an example, so you get a wake up here from the phi side. This one is waking up the switch and probably also starting the PMIC to make sure, okay, this side is supplied. But it is also forwarding the wake up to the phi. In this side, I said, okay, it's just configured to have one port which should be woken up. So communication can be established, and then it might be that later on, depending on what was negotiated on communication, that there's also the ECU needed. So then from the switch side, you have the possibility to also wake up this guy. But this is fully flexible because you do not need to have the microcontroller running if it is not needed. Yeah, let me summarize and conclude. So in general, the zonal architectures bring new challenges because the functions which were separated are now spread over the network. This requires some partial sleep and standby scenarios, so that part of the network or part of the ECU is not active if it is not needed to have it power optimized. And with this, you need to consider in your safety concept that you have this mixed availability of communication, but also the mixed availability of parts in your network being available. And in principle, if you look to this, so if you have a system solution, so which is, for example, combining the microcontroller, the PMIC, but also the communication side, there it can be optimized to support such use cases. Yeah, thank you for your attention.
Thank you for the great presentation. Any questions from audience? Nothing? Okay. That's all for the. Thank you. Thank you. Great presentation. Okay, let's take a coffee break.